Hey everyone, my name's Arnav, and I'm here to give a solution outline to Cram from the 2022 NAC. So in Cram, you're given a string s, and you need to encode it. Now there's two ways to write down characters in s. You can either use 1 byte to write a single character, or you can use a back reference to a previous substring that will always take 3 bytes. And your task is to find the minimum number of bytes needed to encode the string. So as an example, if you have ABC repeated 4 times, you can encode this using 6 bytes. Write out the first 3 bytes, and then use a back reference, which states that the first 9 characters of the string are equal to the last 9 characters of the string. This example highlights that these back references can overlap, saying we've only written out 3 characters, but we can still say that the first 9 characters are the same as the last 9 characters. Okay, so how would you go about solving this problem? Like many NAC problems, there's many different solutions, but this is the solution I came up with. Because this is an outline and not a detailed solution video, I'm going to assume some level of familiarity with each of these things. Dynamic programming, suffix arrays, LCPs, and range minimum queries. Like I said, there's many solutions. You can use a suffix tree instead of a suffix array. There's so many options for solving RMQ problems. But I'm going to assume some level of familiarity with each of these, and I'll just kind of show you how they all fit together for this specific problem. So let's start at a high level, and then we're going to kind of fill in the details as we go down. So first, let's translate the problem statement into dynamic programming formulation. So let min cost I be the minimum cost to encode the first I characters. Now there's 2 transitions from any given for any given I. Either you add the next character, which has a cost of 1 and lets you advance 1 character, or you add a back reference, which always has a cost of 3 and lets you advance some amount, assuming that the substring appears somewhere earlier in the string. So looking at this formulation, there's n states, 1 for each length, but there's also n transitions because you have to consider every substring starting at I. So even if you could somehow tell if a substring appears earlier, this would still take n squared time, which is too slow for the given bounds. However, I claim that for some index I, we only care about the longest substring appearing from I that appears earlier in the string. And you can prove this to yourself with an exchange argument. If you have some optimal solution where at some index I you use a back reference that's not the longest possible back reference, you can always switch it to use the longest possible back reference, and that's only going to make the answer better. Okay, so now our problem is slightly different. Given some index I, what's the longest substring here that appears earlier in the string? And before we solve that, I'm going to introduce some structures and show you how to find the longest common prefix of 2 substrings in sublinear time. So first we build a suffix array. A brief reminder, a suffix array is a sorted list of suffixes of a given string. It's important here that we build this suffix array in sub-quadratic time, because again, n can be 10 to the 5th. Then we build the LCP array, which stores the longest common prefix between adjacent entries in the suffix array. Note that it's just the adjacent ones. In order to find the LCP between 2 arbitrary values, we need to take the minimum over all LCPs in between those 2 elements in the LCP array. So how do we do that quickly? Well, our first step is a suffix array is just a permutation, right? From 0 to n of all of the possible suffixes. So we build the inverse permutation, and we'll call that the inverse suffix array. Then, in order to find the LCP of 2 suffixes, we look up their indices in the suffix array using our inverse suffix array. Then we do a range minimum query over our LCP array. LCP, if you use a sparse table, it's n log n construction and constant time querying. You can use a segment tree, which is O of n construction and log time query. The specific implementation doesn't matter too much here. You just need something that's roughly linear to construct and roughly constant or log to query. And then you can compute arbitrary longest common prefixes in log time. So how is that useful? Why did I go into that digression? Well, this is the problem we're trying to solve. We want to find the longest substring that appears somewhere earlier. Another way of writing this is there's some index I prime which appears before I, and the LCP of I prime and I is maximized. And now we're speaking the language of LCPs, which is useful. So we have this LCP array, we have the list of sorted suffixes, and we want to find. We know that if you look at the suffix array from some index, as you walk in either direction, the LCPs are monotonically decreasing. So for each index I, we need to find the I prime before and after it in the suffix array that are less than I, and compute the LCPs of these. And finding the nearest values in an array is a pretty classical problem that you can solve using a monotone stack. You'll probably have to do two passes here. One to find the nearest value before, and then one to find the nearest value after. One left to right, the other right to left. Okay, so that was so there are several layers to this problem, right? You have to build this suffix structure, and then you have to find the nearest values in the suffix array. But then once you have all of that, you know the length of the longest substring from each index that appears earlier in the string, and the dynamic programming part is actually quite straightforward. You just have two transitions from each index. You either advance by one character or you use this longest substring. So the runtime for computing the dynamic programming is linear, and then the overall runtime is completely dominated by the construction of the suffix array and the LCP array. In practice, pretty much anything faster than quadratic time is good enough for this problem, since the string is only 100,000 characters long. I hope that was helpful, and I hope you enjoyed this problem. Best of luck.